Great, it's recording now. Today we're going to cover section 4.1 related rates. So far we have seen that for quantities that are changing over time, and this is important here, over time, for quantities that are changing over time, the rates at which these quantities change are given by the derivative, right? The derivative sort of captures the instantaneous rate of change of these quantities over time. And I'm going to tell you this straight, guys. All the changes of the quantities for this related rate section will be over time. To put it simple, all the derivatives that we're going to take will be derivatives with respect to time. Okay, now if two related quantities are changing over time, then the rates at which the quantities change, meaning the derivative, right, are also related, right? Somehow should be related, right? And this is actually what you have to kind of show and then answer some questions related to this relationship between the derivative of the quantities with respect to time. Here, an example for you to kind of understand this. For example, if imagine a balloon being filled with air, both the radius of the balloon and the volume of the balloon are increasing. For you to have even a better idea, in our website, if you go to course materials, if you go to important links, you will have access to this animation. Look, this is a balloon being inflated, right? Notice over time the volume increases, but also the radius of the balloon increases, assuming, of course, that the balloon has the shape of a sphere, right? It's a sphere, spherical balloon. So again, you can play around with that animation, right? So in this section, quantities are changing over time, okay? And you gotta kind of in your mind play these animations, right? For different situations, but this is one of the examples. And then once you figure out the relationship between the two quantities that are changing, for example, here volume is changing with respect to time, right? From geometry, we have this relationship, volume 4 pi over 3 multiplied by r cubed. This is how the volume is related to the radius if the shape is a sphere, right? This is what they're saying here, that if the quantities that are changing over time are related, somehow the derivatives of this quantity should be also related, right? This is what I'm saying here. That is why this section is called related rates, right? Related derivatives somehow. And the derivatives are always with respect to time. Now you may say, Professor, where did you get this formula from? It comes from three-dimensional Euclidean geometry, but don't worry, these formulas, if needed, will be given to you, right? What is going to be important is that you should somehow figure out the relationship between the derivatives of those two quantities, in this case, volume and radius, right? Okay, great. Okay, so now let's see an example here, right? Concrete example for you to see how this works. Example 1 says inflating a balloon. It says a spherical balloon is being filled with air at a constant rate of 2 cubic centimeters per second. How fast is the radius increasing when the radius is 3 centimeters? Round your answer to 2 decimal places. Here they are showing you somehow sequence of figures, right? That kind of illustrate this motion, right? I show you in the video. The video is probably better, right? A balloon is being inflated, and over time the volume is increasing, right? As you can see, time 1, time 2, time 3. But at the same time, the radius is increasing, right? Because the volume is related to the radius. Okay, great. Now they're asking you, right? They're asking you, how fast is the radius increasing when the radius is 3 centimeters? Notice this radius is increasing. But at some point, the radius will be 3 centimeters, right? Let's say this is that moment when the radius is 3 centimeters, right? At that moment, they are asking you, what is the rate of change of the radius with respect to time, right? So kind of, we will consider this animation, these motions, but at some point, we kind of in our minds will take a picture. This is the moment when we are taking the picture for this question, when the radius is 3 centimeters, right? At that moment, you will answer the question, right? You will answer, because at every moment, the rate of change is changing, right? Remember the derivative measures the instantaneous rate of change. So at a certain point, you take a picture in your mind, you answer the question. Now, how this is done concretely? Hint here, they're giving you a formula that relates the volume of the sphere, assuming that this sphere, again, is spherical. Assuming the shape of the balloon is spherical, right? This is the formula. V equal 4/3 pi r cubed. Okay. Solution then, solution, right? How to figure out the rate of change of the radius. You start by saying at any moment, here, here, the following is true. The volume is equal to 4/3 pi r cubed, right? Because we're assuming that the balloon is being inflated following a spherical shape, right? Now, we need a relationship between the rate of change, between the derivatives. So a natural thing to do next is this. Take derivatives of both sides of this equation, right? And all these steps will be written out, but now we're just kind of introducing this with this example, right? So the idea is, once you have the relationship between the quantities, you should take derivatives of both sides of the equation. But that derivative should be always, for this section, with respect to time. So dt here always, dt here always, okay? Now here we have the volume. And here we have 4/3 pi r cubed. Next, derivative of volume with respect to time will be just dv dt. Here, derivative of this function with respect to time, notice this 4pi/3 is just a constant, right? It's just a constant. So allow me to take this constant outside of the differentiation, right? Outside of the derivative. And focus on taking the derivative with respect to time of this guy, r cubed. Okay, great. Now, this guy is just dv dt, right? 4pi/3. This guy, I want you to look at it as the following: the derivative with respect to time of this. The function r raised to a third power. Let's write r in red, so you will identify this r as your inside function. It's a composition of functions, right? If you think of this r changing over time. So when you take this derivative, don't forget that since we are taking derivatives with respect to time, you have to start with the derivative of the outside function, which is this, right? 3 coming down, 1 less stays as exponent, r stays as an inside function. But then we're gonna multiply this by the derivative of r with respect to time, right? With respect to time. Remember, the chain rule says that, right? Very good. All right, now, once we have this new equation, this new relationship between the derivatives, right? Derivative of volume with respect to time, derivative of the radius with respect to time. Now, let's substitute what we have and let's solve for what we don't have, right? We have to solve actually now for this guy, the rate of change of the radius, right? That's what they are asking for. Now solve for dr dt. Look, dv dt is the rate of change for the volume with respect to time. That I think is given. Look, they are saying that the balloon is being filled with air at this constant rate, the constant rate of 2 cubic centimeters per second, right? So you pick it up from there, 2 cubic centimeters per second, 2 here. It's a constant rate of change. 4 pi, notice 3 and 3, they cancel. R squared. R, what is R? R, they say, is going to be equal to 3. Aha, is someone noticing the 3, right? Very good, Marcos. Yeah, 3, right? Because they're saying that they want you to kind of freeze this motion when the radius is 3, right? When the radius is 3, remember? Yeah, very good. So the radius is 3 at that moment, right? At that moment, they want the rate of change of 3. And this guy we don't have, right? The RDT. And we have to find it, right? Now we're going to solve for that. So now, basically, just do the math here. 2 equal 4 pi. This is a 9, right? 9 times 4, 36 pi, right? 36 pi. All this calculation. You can do it in your calculator if you prefer. DRDT. DRDT. Last step, solve for the RDT, meaning divide both sides of this equation by whatever you have here next to the RDT. In this particular case, we have this number 36 together with pi, right? So we're going to divide both sides by 36 times pi. Here, notice this will cancel, giving us an exact answer first, in case you need the exact version of this. 2, dividing this by 2, dividing this 36 by 2. 2 into 2 is 1. 2 into 36, 18 pi, right? 18 pi. This should be the exact version of the answer, right? In the end, feel free to attach the units, centimeters per second, right? Yeah, done. But since we are dealing really with this practical problem, real life problem, the real world problem, most of the time, this should be computed as a decimal. So let's do it together. Let's bring out our decimal scientific calculator. 1/18 times pi is just 0.01768. They say round it to 3 decimal places, right? So we go up to here. This 7 becomes 8 because of the 6, right? So it will be 0.018. 0.018. And in the end, attach the unit centimeters per second, right? Per second. That's it. That should be the rate of change. So you can say that the radius is a conclusion, right? The radius is increasing, right? Positive rate of change, right? Increasing at the rate of, at this rate of 0.018 centimeters per second, right? At that rate. Positive rate means increasing. Okay. All right, guys. So now we kind of use this problem as example, right? The other examples that we're going to deal with are similar, but mathematicians can figure out a set of steps, a set of hints, guidelines, so that if you follow them, it will help you to solve these related rate problems. And these steps are, first step says, draw a diagram if needed. In this case, the diagram was already given, right? But you yourself may need to draw a diagram. You will see when the examples are coming up. Step 1 or hint 1. Hint number 2, figure out, after you draw the diagram here in step 1, and identify variables and constants, right? What is changing, what is not changing over time is what you have to identify, right? And choose some variables from the English alphabets to identify those quantities. Often we will use X, Y, and Z, but feel free to use any 3 letters or 2 letters from the English alphabet. Hint 2, figure out an equation relating the variables and the constants. In this case, the equation came from a 3-dimensional Euclidean geometry, right? This was the equation was given. Sometimes we'll be given the equation, but if not, we will not be hard to figure it out. I will show you. How to find the equation. Hint 3, take derivative with respect to time of both sides of the equation, right? Always the derivative with respect to time, always. And the last hint, solve for the rate that you're looking for, right? You will always look for a rate. You have to solve for that rate, right? Replacing everything that you know. And that way you will end up with an equation. Solving for your rate, you will be done. Here is another example. The ladder problem. But before we go over this example, let's see if we can practice a little bit, okay? Based on this first example I gave you. Let's go here. And let's try to follow the guidelines. Let's start with this, number 1. Can you try this? Here, they're saying that suppose that we have that the radius of R and the circumference are related by this formula, right? Circumference of a circle. They say write an equation that relates the derivative of the circumference with respect to time with the derivative of the radius with respect to time. Hint, take derivatives in both sides and see what happens, okay? So try this, guys, and then we will do it with these tools. So kind of we will warm up for the next example. Take derivatives with respect to time and see what happens. What's the relationship that you get? Try guys, and if you find it, let me know. I see there's some activity on the chat room. Marcos, excellent. Yeah. So if we take derivatives on the left side of the equation, we're gonna get here derivative of C with respect to T. Not much to do there, right? But here, notice this 2C is a constant, comes out of the derivative to pi. And then you are left with this derivative, right? Derivative of R with respect to T. That's it. If you want to kind of take the derivative is 1 times the RDT, same, right? So the answer for this, sometimes students put here 1, I don't want to confuse anyone, 1 times derivative of R, right? The derivative times minus 1, but then must be multiplied by the RDT because of the chain rule, right? Because we are taking derivative with respect to T, not with respect to R. So this in simplified form, very good, leads to choice A. Very good, this one. Very good. This one we just did, but let's make sure that everybody understood. Try to do this now. Number 2. Suppose that the radius R and volume V equal 4/3 pi R cube of a sphere are differentiable functions of T. Write an equation that relates dV dt with dr dt. Can you do that? I'll give you the hint as usual. 3 pi R cube. Take derivative here with respect to time, always our derivatives, right, for this section. And here take the derivative also with respect to time. And see what you get. Leave pi alone. Don't substitute pi for 3.14. Leave pi alone. They want it there. So somehow, let's see. Take a look at this. Marcus, very good. Yeah, that's what it is. Very good. Yeah, on the left side, not much to do because this is just dV dt, or if you prefer, the derivative of V is 1 times dV dt. It's the same, right? It's just this. Over here, however, since you have this constant 4 pi over 3, take that constant out. This is a real number. And focus on taking this derivative of R cubed, but with respect to time. This leads to the following: dV dt 4 pi over 3. This derivative, the number 3 comes down, right? As a derivative of outside function. You have to consider here 3 down, and then something raised to a second power. What is that something? The inside function, right? And then you have to multiply this by the derivative of the inside function. You have to attach this dr dt, right? Because we're taking the derivative with respect to t, not with respect to r. All right, and then just simplify, right? Notice these 3 and these 3, they cancel. I just clear up and the answer should come out there. 4 pi, 3 was canceled, r squared, dr dt, right? This is how the derivatives, the rates of change are related, right? Yeah, so this is, yes, for number 2, this guy. Excellent. Very good, guys. So now that we know how to go from the relationship between the quantities to the relationship between the derivatives, let's go back to the lecture and let me show you the second problem, the second example. It's called the ladder problem. Very well known. It's a classical problem when covering this topic of related rates in calculus, the ladder problem. Example 2, it says, a 10-foot ladder is leaning against a wall. If the top of the ladder slides down the wall at a constant rate of 2 feet per second, how fast is the bottom of the ladder moving along the ground when the bottom of the ladder is 5 feet from the wall? Okay, so imagine this is a wall, this is the ground, and this is the ladder, okay? Now, the ladder is 10 feet, the ladder, 10 feet long, right? And in the guidelines, they say, right, draw a diagram. Let this be the diagram, right? Wall, ground, ladder. This ladder is it's falling right in this way. The top of the ladder is falling at 2 feet per second. And as a consequence of that, the bottom of the ladder is moving to the right, right? We don't know at what rate, we will find out, right? That's actually the question, right? But for you to kind of understand this better, again, in our website, I have attached this, I have made it available for you to see this animation under course material, important links. Look, imagine this is the ladder, right? That we have represented here. The top is falling at 2 feet per second. But as a consequence of that, look, the bottom of the ladder moves to the right, right? Moves to the right. And notice the speed at which it is moving to the right may change at every moment, right? But what they are asking there is to find out is what is that rate of change, right, of the bottom of the ladder with respect to time when this bottom point of the ladder is 5 feet away, 5 feet away from the wall, right, from the wall. That's what I say. At that moment, you kind of take a picture in your mind of this motion, right? I said, at this moment, I have to answer that question, right? That's what we'll do. Okay, so imagine that moment when the ladder is the bottom of the ladder is 5 feet away from the ground is here. Say at this moment, this is 5 feet. Yeah, at that moment, we have to answer the question, right? What is the XDT? But in order to write the XDT, I better label my quantities that are changing, right? This quantity, the one that measures the height, I will represent it with Y. This quantity, the one that measures the length or the distance from the bottom of the ladder to the wall, I will label it with X. So basically they are asking me at this moment, right? At this moment, what is dx dt right there? And this is what we're gonna do. Now, I mentioned variables and constants. This guy the length of the ladder is a constant, right? Never changes throughout time, right? Constant. However, the height and this length, the length of the distance from the bottom of the ladder to the wall they change all the time, right? This variable, in case you want to kind of differentiate variable from constant, right? Variable, this is also variable, right? Yeah. All right, once you have identified your variables and your constants, right? Then you go ahead and say, okay, at any moment, there is a relationship between X and Y, right? Anybody could tell us what is that relationship between X and Y, looking at this figure? Anyone in the chat? There is a relationship between X and Y and the length of the ladder 10 at any moment. See in the chat? Marcos, yeah, you got it. Yeah, you may have Miguel also, right? Yeah, so the Pythagorean theorem, right? Yeah, no matter in which position the ladder is, this angle will be always 90 degrees, right? Maybe we should write it. And because of that, the length of X and Y will be related by this equation, X squared plus Y squared equal 10 squared, right? It's called the theorem of Pythagoras. Yeah, very good, excellent. Yeah, this will happen at any moment, right? Now we have the relationship between the quantities that are changing over time. Let's follow the guidelines. The guideline says, then take derivatives of both sides of this equation with respect to time, right? With respect to time. So always derivative with respect to time. All right, now this is going to be X squared plus Y squared. And this 10 squared is just 100, right? It's just a real number, constant. Now, go ahead and take derivatives of these two guys, of the sum of these two functions with respect to time. We start with the derivative of X squared. The derivative that comes to mind is 2X, right? But since we are taking derivative not with respect to X, with respect to time, we have to attach this dx dt, right? It's the derivative of the inside function X. Plus, now the derivative of Y squared. The derivative of Y squared, the derivative that comes to mind is 2Y. But that would be if we had taken derivative with respect to Y. We're taking derivative with respect to time. So you're going to attach dy dt. Don't forget about this. Now, anyone could tell me what is this derivative? The derivative of 100 with respect to time? I see in the chat. Very good. Excellent. Marcos also, right? Yeah, you guys made my day. This never changes. The length of the ladder never changes over time. It's a constant function. So 0, right? Derivative 0, derivative constant function 0. Excellent. All right, so you can see, right, from the relationship of the quantities changing over time, now we are at a new relationship here between the derivative, between the rates of change, right? Very good.
Professor?
Yeah, go ahead.
I have a question. I don't understand the logic of why you said we have to input dx by dt and dy by dt. Like before we opened the formula to solve x squared plus y squared, didn't we already say we're taking it in respect to time? So why do you have to attach that at the bottom?
Wait. Yeah, very good question. So let me explain here on the side, okay? When you are taking the derivative of this, let's say x quantity, right? The distance from the bottom to the wall, we are doing this, right? Derivative of x with respect to time, right? And this is a square. So I want you to think of this as a function x that depends on time and an outside function, the square function. So according to the chain rule, you're supposed to do this group 2. Derivative of the outside function is this, right? Keeping the inside function x times derivative of x with respect to t, right? This is when you take derivative with respect to t. Maybe in your mind, note, this is what kind of is happening. if I am taking a derivative of this with respect to x, then yes, this will be s to x. You follow? Look, this is to x, but since this derivative with respect to time, not with respect to x, look, I have to attach this guy. Better now? Right?
Yes.
Yeah.
Okay.
Yeah. Better now? Yeah. And the same time, the same thing with y, right? The derivative y squared will be, with respect to y, will be to y. But with respect
Right.
to t, we have to attach. Yes.
So that
Very good.
technically means we didn't find it in respect to time. Like, what is? I'm sorry. I think
yeah,
I'm
it
confusing
technically,
myself.
no. Yeah, it technically means that this guy has to be found.
Right.
Has
So
to,
we
will
didn't find it. Yeah.
No,
Okay.
no,
Okay.
yes, no, yeah, no,
Okay.
yeah, very good question too. Yeah, no, we have to find it, right? Yeah, excellent.
Okay.
Yeah, so now we are going to replace everything we have and we are going to find, right, what we don't have. So here, for example, x, right? Do we have x? Anybody could tell us what is x? Well, I think it's here, right? Yeah, they want this when the ladder is 5 units away from the wall. So this should be 5, right? For this one, we have 5. Dx dt, we don't have. And indeed, the question is this, right? What is the, look, how fast is the bottom of the ladder moving along the ground when the bottom of the ladder is 5 feet from the wall? So this we have to find. We don't have it, right? We don't have it. Twice here, y. Do we have y? Let's see, right? Look, at this moment, right? At this moment, let's just kind of retrieve that triangle here at this moment, right? When x is equal to 5, when x is equal to 5, right? When at this moment, we kind of take a picture in our minds, right? Remember maybe this will help. This ladder is falling, right? But when it reaches 5, right there, they want you to answer the question, right? So right there, look, this is 10, this is 5. It's possible to find this with the theorem of Pythagoras, right? It's possible, so let's do it. So when x is 5, since the length of the ladder is 10, 10 is there, then it's possible to find y. How? Well, using the theorem of Pythagoras, right? Y squared plus 5 squared, 10 squared, y squared, 25 equal 100, right? Subtracting both sides 25, we get y squared equals 75, and y should be equal to the square root of 75, right? It was possible to find it. And that square root, guys, you can find it in your calculator, right? Your calculator. For these problems, typically, they don't want exact solutions. They want decimal solutions, right? Approximated solutions. So 8.66, right? You can see, we're going to write 8.66 feet for this, 8.66 feet. Then when x is 5, when you take a picture in your mind of the motion, this guy should be 8.66, right? Because x and y are related by the theorem of Pythagoras. Now, this is precisely, guys, believe it or not, what you're going to put here, okay? 8.66. Great, we got this guy. dy dt. What is dy dt? I see someone wrote something on the chat. dy dt now. dy dt. Marcos is asking, right? Can I write just the square root of 75 or 5 times the square root of 3? Also, you can write it, Marcos. It's absolutely okay. It's okay. It's up to you. It's just that here, the computer in the homework will allow you to use these decimal representations as long as you approximate them as they are asking to approximate it, right? We are using just 2 decimal places. It should be fine. Either way is fine. Very good. Now, anyone could tell me what should be this dy dx based on the problem, the information of the problem. They are saying that this guy is falling at this rate, right? But what number is it? Great, 2, right? But something else is missing there. Notice that this y throughout time is decreasing, right? It's getting smaller and smaller, right? to the point that at a certain point it will be zero, the y, right? So it's the for you to see. Look at y. It starts there, but decreases over time, right? It's decreasing over time. So it will be 2 the rate, but in reality, mathematically, we should write -2. And this is something that I want you to pay attention to. When the quantity is decreasing over time, you have to attach a minus there because it's a negative rate of change. Okay, it's decreasing over time, -2. Finally, look, now everything is ready for us to solve for dx dt, right? So now solve for dx dt. Basically isolate dx dt, right? Yeah, maybe the 4 here, solve for dx dt, and that's it, that will be it. All right, so let's do that together. 10 times dx dt here. Here, all this multiplication, we can get it in our calculator, right? You don't have to do it in your head. 2 times 8.66 times -2. Negative 34.64, right? Negative 34.64. So let's write it here. Negative 34.64. Very close to the end. Add now this to both sides of the equation or transpose it to the other side. Changing its sign, right? You end up with this, right? 34.64, and dividing both sides by the number 10 will finally give us the answer, right? That we were looking for. Look, dx dt equal 10 into this guy is just 3.46, right? Or you can use your calculator and get it, right? You just have to move the decimal point one place to the left, or you can get it in the calculator. In the end, guys, feel free to attach the units. We were measuring the distances in feet, time in seconds, so feet per second, right? This is it. This is the answer, and it makes sense, came out positive, consistent with the fact that this x is increasing over time, right? Look, increasing over time. So positive rate of change, okay? Yeah, so everything clear? Any questions about this ladder problem?
Professor?
Maybe yes, question?
Sorry, yeah. My question is that, so you put -2 because you said that it's going to fall at, like, it's going to continue to decrease our y value, right?
Yes, exactly,
Okay.
precisely, because it's decreasing. Yeah, go ahead.
Right.
Yeah.
So if the question was phased in a way that the ladder's on the ground and we're bringing it to height, would our 2 be positive then?
Absolutely, yes. Let's say
Okay.
you are pushing, someone is pushing the ladder here and it's going up, then it will be +2. Yeah, good question.
Okay.
Yeah. Yeah, you
Okay.
gotta put you guys gotta put yourself in different scenarios, right? Yeah, very good.
Mhm.
If someone is pushing the ladder, of course, this will be positive. But I'm gonna write a note here, precisely because that note here justifying this negative sign. It is negative. It's negative because y is decreasing. Is decreasing over time. Decreasing over time. Okay, decreasing over time. Yeah, very good, guys. Very good. Excellent. Yeah, so now decreasing over time, right? Very good. Yeah, next, let's practice now. Remember, guys, practice makes the master. So let's practice now. Let's this is similar, so let's do a ladder problem. This problem, guys, you should know how to do it. The ladder problem right away. So can you try this on your own? And then probably we will do also the balloon problem to reinforce. Yeah, a ladder is falling again. Yeah, in the home we probably will have a different situation there, but in this case, still falling, right? A ladder is slipping down, vertical wall, right? So a diagram helps, right? So let me just give you a hint this, right? It's falling at this rate now, 4 feet per second, right? Falling. And as a consequence of that, this guy is moving to the right, right? It's moving to the right. They want you to figure out what is this guy, dx dt, right? When x is equal to, when this x, let's call this x is y, when x is equal to 16, right? Because it says moving along, how fast is the bottom of the ladder moving along the ground when the bottom is 16 feet from the wall, right? 16 feet from the wall, 16 feet from the wall. Yeah. You follow, guys? Yeah, let's try to do this. And well, the other hint is that this is 20, right? The length of the ladder never changes, right, throughout time. So the last hint will be this: at any time, because of the theorem of Pythagoras, x squared plus y squared equal 20 squared, right? 20 squared. Yeah, that's the theorem of Pythagoras. The next step is take derivatives in both sides, right? Yeah, let's take this, the last hint. Take derivatives on both sides with respect to time, right? And remember, don't forget to attach that dx dt, that dy dt, right? Because we are taking derivatives with respect to time. Very good. Excellent. Very good. Very good. Very good. Try, guys, to give it a shot. And let me know if you finish. Yeah, maybe I should put here that they are asking you the question. Right, yeah, right there. Dx dt when x is 16 feet. Very good, right there. And if you have any questions, just let me know, okay? Along the way. I see. Some activity on the chat room. So let's see. Marcus. Excellent job. Very good, good work. Excellent. You got it. Very good. Yeah. Yeah, let's wait a little bit so we get a chance to figure this out. Yeah, this problem is a beautiful problem and a classical problem on rates, right? It has some variation. I have attached in the homework problems a lot of videos for this part because some problems are really tricky. So in case you get stuck on the homework, watch the 5 minutes video and it will give you a hint. Good.
I got 3-2, Professor. D. I got that as well.
Oh yeah, you made my day. Excellent. Yeah, you see, it's not. Yeah, so I'm sorry. I'm sorry,
it's
Ma.
Okay.
Yeah, it's just that I don't see your name on the screen, but here I can see it's Ma. Yeah, excellent, right? So it means that you got it. It means that you understood. Miguel also figured it out. Yeah, but I'm glad. Yeah, it's not trivial, right? It's tricky. There's science involved, but once you get a hand of it, it should be fine. Great. Let's do it together, right? Yeah, at any moment, x squared plus y squared equal to 20 squared. And this 20 squared, no, how to say, is 400, right? So when you take the derivatives, this is going to be the derivative that comes to mind, 2x, right? Dx dt, right? Remember, you have to attach this guy because we're taking derivative with respect to time, plus derivative of y squared. The derivative that comes to mind, 2y, but then we're going to attach dy dt, right? And what's the derivative of this guy, 400, the derivative of the length of the ladder? Anybody could tell us?
0.
0, right? Yeah, that's it. Because the length of the ladder doesn't change over time, right? No change, no derivative, 0. No, right. Okay, great. Excellent. Now it's time to substitute what we have and find out what we don't have. X we have. At this moment, they want you to take a picture in your mind, right? So 16 is this X. Dx dt, we don't have it. Actually, we want to find out what is this, right? At this moment. Plus twice y. What is y? Well, it seems like we don't have y, but in reality, think about this. If this is 16 and the length of the ladder is always 20, this guy can be found. And I explained this in details before, but right now I'm just going to write the formula from the theorem of Pythagoras. Hypotenuse squared minus this guy squared, right? And you can compute this in your calculator. I think it's even exact. Yeah.
12.
There you go, 12, right? Yeah, very good, very good. Let me just show how you can get it in your calculator. And it came out exact, right? Sometimes it will be exact, but if it's not exact, I just show you before that you just round it to 2 decimal places, right? 12, exact, excellent, right? Very good, 12. And then this 12 feet, right? Now, so this says that when x is equal to 16, then y has to be 12, right? Because they're related, 12 feet, right? And this is, believe it or not, guys, what you put here, 12 feet, 12. Very good. Now, question for you guys. What are we going to write here for the dy dt? Anybody?
-4.
-4. Excellent, excellent one. -4, because again, notice that the y throughout time is decreasing, right? To the point that when the ladder completely on the ground is 0, right? Decreasing. So minus, this requires this -4, right? Be careful there. All right, then next is just algebra, right? This is 32 dx dt. You can solve this equation any way you want. Minus, this is 2 times 1224 times 4, 96, right? 0. And then add 96 or transpose it to the other side. Any way you want to solve this equation. 32 dx dt equal 96. And finally, then dx dt should be this, right? 96 over 32. And when you put this in your calculator, 96 over 32, notice it's just 3, right? 3. Very good, 3. So this is 3 feet per second and came out positive, consistent with the fact that x grows over time, right? Grows. So 3, then you go here and you choose this one, right? Very good, excellent. Feet per second. Very good. Okay, guys, we mastered a ladder problem, but now we need to master other forms. What other forms are you talking about, Professor? Well, for example, this is another nice form. Yeah, this for you to do at home. Yeah, go ahead.
I'm sorry, I have another question.
Sure, yeah. Go ahead.
You said dx over dt is like positive. I don't know. I'm thinking as because I think of rate of change, right? It has to be like a slope. Our x is horizontal though. Yeah,
but yeah, it's a very good question, right? The ladder right. Gets horizontal. The ladder, right? But if you graph this function x in terms of time, notice that x started at some distance, right? And it's increasing. So most likely the graph of x will be like something like this, right? Increasing. And what this is saying is that at the moment when x is 16, the slope of this tangent line, right? The slope of this tangent line will be 1 to 3 to 1, the slope, right? Don't look at the ladder because the ladder is not going to determine the graph of x, right? This is x, this is time. If you graph second by second, x versus time, you will get some increasing function, right? Because this guy is increasing. Maybe even a line, well, I don't know. In general, a curve, but perhaps a line, given that this is constant, right? You follow?
Yeah,
so okay. Yeah, don't look at the shape of the ladder
Diagram we have?
instead.
Yeah.
So just look how x is changing over time. Okay.
Okay.
Now let's look at other forms, right? For example, let me show you number 6, and then I will ask you to do number 7, which is similar. Look at this problem. It says water is falling on the surface, wetting a circular area that is expanding at the rate of 2 square millimeters per second. How fast is the radius of the wetted area expanding when the radius is 152 millimeters? Round your answer to 4 decimal places. All right, following the guidelines, I'm going to draw a diagram that more or less is going to capture what is happening here, right? Water is falling, right? And as a consequence of that, on the ground, wetted area is this, right? There's a radius here. The circle is expanding, the radius is growing, right, over time, the area as well. Now they are asking you to figure out what is the RDT when the radius is 152 millimeters, right? So try to figure out how the area is related to the radius for a circular shape. Not hard to see that this is area equal pi r squared, right? If you don't have this formula, you might memorize it or write it down somewhere. Area of a circle is pi times r squared, right? It starts with that. Now, the second step is we are supposed to take derivatives of both sides of the equation with respect to time, right? With respect to time, to figure out the relationship between the rates of change. Let's see what happens. Now, this one, this is gonna be just dA dt, right? It's gonna be just this, right? And it's actually given because they say that the circular area is expanding at this rate, right? So we have this. But here, notice pi is a constant, so comes outside of the derivative, and I should focus my attention on this derivative of r squared. Now, here, dA dt, derivative of the area with respect to time, equal pi times this guy, derivative of outside function to r, the derivative comes to mind, right? But since we are taking the derivative with respect to time, this should be the r dt, okay? Once you have the relationship between the derivatives, substitute what you have and find out what you don't have. Notice that this part is given. Here, the circular area is expanding at a rate of 2 square millimeters per second. Expanding. Expanding means positive, right? Positive rate of change, right? So I gotta write just 2, expanding. Pi, 2 times r. What is r at that moment? When you take the picture to find the rate of change of r is 152. So we're right here, 152, right? And this is the only quantity that is unknown. It's actually what you have to find, right? Have to find. So at that point, this shouldn't be difficult because now, next, you simply divide both sides of this equation in order to find the RDT, in order to isolate this, by whatever you have here, right? Next to this guy. In this case, it is this, pi times 2 times 152, right? I'm going to divide both sides of this equation by this quantity, pi times 2, 152, okay? This will cancel this. dRdt should be equal to this. Let's take our calculator, right? And let's follow the instructions. They say round your answer to 4 decimal places, right? 4 decimal places. So we do 2 divided by pi times 2. Notice how I'm using parentheses, so I don't have to write the multiplication symbol. 152. 0.00209. They want this rounded to 4 decimal places. So this 0 becomes 1, right? So we have to write 0.00201, right? And in the end, we may attach units, square millimeters per second, right? We are measuring the areas in square millimeters and time in seconds. Positive, came out positive, consistent with the fact that the radius is increasing over time, right? Increasing over time, so that's good. Okay, guys, so now based on this, Can you try number 7? Try this. Not that difficult. Yes. Well, I will leave it there, okay? So you can check it out. The formula area pi r squared, right? Pi r squared. This is also helping your homework, which you have in your account already by now. Yeah, try that. Yeah, and the answer here was this. Yeah. Notice this is the variation of the radius, so we don't need this, right? Yeah, it's just millimeters per second because it's the variation of the radius. Be careful that I was still thinking of area. I think it's just millimeters per second. Water is falling, right? Yeah, not an artist, but I'm kind of doing my best to recreate this, right? If water is falling, this is what's going to happen on the ground, right? You will see some circular shape there. And what is important here is that the radius of this circular shape will grow, right? As the area grows, right? So if you represent the area of this circular region with A is related to the radius this way, A equal pi r squared, right? At any time. All right, but now we need to find out the relationship between the derivatives of this radius and the area, right? For that, we take derivatives of both sides with respect to time, right? Always this derivative with respect to time for related rates. Here, I'm gonna get derivative of this is 1 times dA dt, right? This is just this, and it's actually given. Here, take your pi outside, focus on the derivative of r squared. But the derivative of r squared, the derivative that comes to mind is 2r, right? But since we're taking derivative with respect to t, you gotta attach this dr dt. At this point, substitute what you have and find out what you don't have. We have the variation of the area with respect to time. It says here that this is expanding at the rate of 7 square millimeters per second, expanding. So positive, right? I'm gonna write plus here. Look for expanding, positive. Pi times 2r, the radius, they want it to be 101, right? At the moment when you kind of in your mind take the picture of this motion. And at that moment, you have to find this dr dt. Now here, not hard to divide both sides by pi times 2 times 101. Here the same, and using the calculator, we should find our number, right? We're looking for our rate of change, dr dt. So dr dt should be the following. Take your calculator, your Desmo scientific calculator. Strongly recommend you to use, guys, because it's free. It will always be free. It's OER material, right? So 2 times 101. And remember, follow the rules for the rounding, right? I think it says rounded to 4 decimal places. So let's do that. And if you do the rounding, you will find that this ends up being 0.0110, right? 110. So 0.0110 millimeters per second, right? In the end, feel free to attach your units. And that corresponds to choice. This is right, very good. Yeah, excellent, guys. So this is another form, right? Another situation for related rates. Let's explore other forms. I had this one with a shadow. Yeah, but let me secure the ones that I really want you to understand. We're flying a kite. Yeah, let's do this one with the man flying a kite, okay? Let me explain this to you first, and then I will let you do the next, okay? I will let you do the next. So it says here, a man flies a kite. Let's draw a diagram here of a man flying a kite. At a height of 120 meters, at a height of 120 meters. So this is the height, and it will be always 120 meters, right? It's a constant, 20 meters. Yeah, now the wind carries the kite horizontally, right? It's moving it horizontally in this direction, away from him at a rate of 10 meters per second, 10 meters per second. So as a consequence of that, the kite at any other moment may appear here, right? So this is the kind of the general diagram. All right, so now, and this is always 120 meters, right? Now, how fast is the distance between the man and the kite changing when the kite is 130 meters away from him? 130 meters away from him, right? Look, I want you to pay attention to it. 130 meters away from him. And here, the wind carries the kite horizontally away from him, right? So basically they are saying, right, how this distance between the kite and the man is changing when the kite is 130 meters away from him. So it's 130 meters, right? Very good. All right, let's find out, right? But for that, we need variables. The distance between the man and the kite is changing all the time, right? Let's represent that distance with the letter Z, Z as in zebra, right? Z. And let's represent this horizontal distance now with X is changing. The vertical distance is not changing, right? It's always 120 meters. So this one, 120 is not gonna change. All right, so now we can say, right, at any moment, what is happening here? At any moment, look, this will be Z, this will be X, the Y will be 120, right, at any moment. So what is gonna be true is that X squared plus Y squared, but Y is a constant, 120 squared equal Z squared, right? Z squared, the distance between the man and the kite, Z squared. This is our equation between X and Z. Now we want the relationship between the derivatives. Not a problem, just take derivatives with respect to time of both sides of the equation, right? Of both sides of the equation. Yeah, this way. Derivative here of X squared is 2X, the derivative comes to mind, but since we're taking derivative with respect to time, we have to attach the X dt plus. Who can tell me what's this derivative? Derivative of 120 squared. 120 squared is just some number, right?
0.
0, right? Excellent, right? Nothing. And this one should be 2z dz dt, right? You follow, guys? Yeah. So this disappears. So now time to replace what we have, right? Substitute what we have. X we have, right? They want this at the moment when X is 130. Dx dt we don't have. We have to find out what it is, right? 0 disappears. 2 times z. Z, do we have z? Well, when this is 130, when this is 120, z is determined, right? Z is determined. I'm gonna write here, z. When this is 130 and this is 120, z will be the square root of 130 squared plus 120 squared, right? According to the theorem of Pythagoras. And that can be calculated. We can figure this out in our calculator. Let me show you here. So 1 square root of 130 squared. This time probably it's not going to be exact, but that's not a problem. Just round it to 2 decimal places, should be fine. Yeah, I get this 176.91. 176.91. Just to play safe, I'm going to take 3 decimal places, okay? 176.918. 176.198, right? 198 meters. This is what I'm going to write here for Z, right? For Z. 176.198. And the last one, dZdt, I don't have, right? dZdt I don't have. So we have to find out what actually, this one I think I have. The horizontal distance is changing at 10 meters per second. So this one, this is the one that we don't have, or one we have to find out. So this one we have, the dx dt, the variation, the horizontal distance with respect to time is just 10. I'm taking this positive because notice it's growing, over time. So in the end, dCdt will be what? We just have to just divide this into this, right? Into this. So let's take the calculator, let's do that together. So 2 times 130 times 10, right? Times 10, all divided by 2 times 176.198. You may say, Professor, the 2's can be canceled. Yeah, you can cancel that, but just in case it's 2, this is 3, better just do it in general, right? Yes. So I got 7.25, 7.25, which can be rounded to 7.3. I see that the answer has been rounded to 1 decimal place, right? So 7.3, it's approximately, it's going to be equal to 7.3. In the end, you attach the units, meters per second, okay? So that's it. As you can see, it's a variation of the previous problem, but follow it. It's not that difficult, really. Very good, guys. Yeah, this problem 11 is similar. So I'm going to leave this for you to do at home. Instead, I'm going to try to go over other forms, right? That you're going to need for your homework and perhaps for the exam, right? That's coming up in November, I think. All right. So this guy is similar to 10. So you can do it at home, but let's explore this other form.
Professor, I have a question.
Yeah, sure, Ma. Go ahead.
So you said we have dx by dt. Can you show me where the rate of change of x is the horizontal line?
Yeah, because here, but you see that it says here, right? A man flies a kite this high, and the wind carries the kite horizontally away from him at this rate, horizontally away. So this rate, 10 meters per second, is this, right? This distance x is growing at this rate horizontally, right? Yeah, I know. The kite is moving at that rate, right? But since the kite compared to this guy, to the distance from the only difference is a constant. The difference of this part, this initial distance, will be the derivative will be 0. So that's why I took it directly from there. Okay. You follow?
Right. So we're finding the rate of change of the diagonal line.
Yes, of this diagonal line, this z. Yeah. This rate of 7.3 meters per second means that this line is growing at 7.3 meters each second, right? Very good. Yeah. We are finding that the rate of change of this z, this distance.
Okay.
Excellent.
Okay.
Yeah, very good. Yeah, this one, guys, I think is similar. You can try it at home, or we can go back to it once we go over the other forms that I want to secure. So I'm going to explain next this form, which is a little bit tricky, number 12. And I will ask you to do number 13. You will have to do it to practice, okay? Yeah, it talks about 2 airplanes. One airplane is approaching an airport from the north at 182 kilometers per hour. A second airplane approaches from the east at 294 kilometers per hour. Find the rate at which the distance between the planes changes when the southbound plane is 31 kilometers away from the airport and the westbound plane is 25 kilometers from the airport. Now, let me explain this nicely. First, let's draw a diagram, right? A diagram. Let's say this represents the north, south, east, west. They talk about 2 airplanes, right? One of them is coming from the north, right? At this speed. Let's say here is the airport. Okay. At this speed, 182 kilometers per hour, right? Per hour. Yeah, this direction. A second airplane approaches from the east, from here, right? A second airplane, let's choose another color, let's say this, and then at this speed, 294 kilometers per hour. Okay, this way. They're both headed to the airport here, right? Now, as they move, right, there is going to be a distance between the two of them, right? A distance, which is going to be this distance, right? This distance. Let's represent that with Z again, right? This distance. And at the same time, there's going to be a vertical distance from the airplane to the airport, the one that's coming from north, the one that's coming from east. Let's represent this with X, okay? So 3 variables, as you can see, right? And the 3 of them are changing. No variable is constant this time, right? The 3 of them are changing. But however, at any time, the equation, what should be, do you think, the equation here for these 3 variables that are changing? Anybody in the chat or verbally?
Z square is equals to X square plus Y square.
Excellent, Matt, right? The theorem of Pythagoras still holds, right? Excellent. At any time, X squared plus Y squared equals Z squared, right? Everything is changing, but at any time, this is true. Now, what they are asking you to figure out is this. They say, right? Find the rate of change at which the distance between the planes, the rate of change of Z again, right? Changes when the southbound plane is 31 kilometers away. So 31 here, right? And westbound plane is 25 kilometers away from the airport, right? At that moment, right? At that moment, they might be like this, right? Not necessarily parallel to it, right? I don't want to make it parallel, right? Maybe one is moving faster than the other. So maybe this figure will be like this, perhaps, right? Who knows? But at that moment, there's going to be another Z there, right? At that moment, they want you to figure out dz dt, right? That's the idea. That's the idea, guys. All right. So we follow our technique, right? We take derivatives of both sides of this equation between these quantities that are changing with respect to time, right? And let's see where we'll end up. So this derivative is 2x, the derivative that comes to mind, dx dt, right? Dx dt plus. This derivative should be 2y dy dt, right? Dy dt. And who can tell me what's this derivative? Anybody? The derivative of z squared.
2z dz dt by dt.
Excellent, Matt. You made my day. 2z, right? Before it was constant, right? Some of them, but this one, all of them are changing. So this will be 2z. Yeah, worth it to write it nicely here. 2z dz dt. Excellent. Now, guys, let's replace what we have as usual, right? And let's find what we don't have. X. What is X? Well, X, this is 25, right? Because this is the X distance when they want you to take a picture in your mind and find out what's the variation of this Z, right? Who can tell me what is dx dt here? This guy. Anybody? In the chat. Yeah, Marcos. Yeah, Marcos, but 182, I think, is the one
the y
coming down y. Here. Yeah, yeah. The for y, yeah. Where need for x? What would be for x? Let's see.
294.
Very close, 294. But notice that x is
negative,
decreasing over the negative. Yeah, be careful there, guys. A lot of tricks here. 294, but negative. Why? Because this x is decreasing over time. As you can see, right? The airplane is getting closer and closer to the airport, so the x distance is decreasing. All right, so very good. Now, what should be then now this other guy? 2 times y. Y is clearly, they say 31, right? But the one that I want you to find out is this. What is this? dy dt at that moment. Anybody?
Negative 182.
Negative 182. Excellent, right? Negative because also y is decreasing over time, right? As you can see. Yeah, very important, these signs, because otherwise it's not going to work. Here 2z, what is z there? Well, we have, let me isolate this triangle, right? We have this situation here. We have that this side is 31. This side is 25, right? 25. At that moment, it's possible to compute z, right? Looking at this right triangle, right? So z at that moment, when y is 31 and x is 25, because of the theorem of Pythagoras, has to be equal to this, the square root of 25 squared plus 31 squared, right? So we can compute this in our calculator. So let's do that together. So a square root of 25 squared plus 31 squared. 39.82. All right. Since I want to play safe, I could take 3 decimal places, but 2 probably would be enough, right? Let's see what happens if we take just 2. 39.82, 39.82, okay? 39.82, 39.82. This is measuring kilometers, right? This is what you have to put here. I will just put right there. 39.82, okay? And dz dt is what we need to find, right? dz dt. Very good. Now, guys, I'm gonna do this in one computation, okay, but slowly, so everybody will see. Look, what is needed here? I'm supposed to compute all this first, right, in the calculator, and then divide this part into this, right, into this. Let's do it in one computation. So you take your calculator, scientific calculator, you start with this side, the left side, right? 2 times 25 times negative, don't forget the sign, negative 294 plus 2 times 31 times negative 182, right? Notice how I'm using parentheses. I don't have to write a multiplication symbol. And all this, look, highlight all this, slash, 2 times this guy, right? 39.82, 39.82, 39.82. Let's see what happens. I got negative 326.26, right? 27 rounding. But I think they want you to round it to the nearest whole number, because I see I see that all the answers are whole numbers, right? You can see whole numbers, So let's round it to a whole number. If you round it to a whole number, this will be negative 326, right? Negative 326. Let's do it. Negative 326. In the end, feel free to attach the units for distance kilometers, for time hours. So it will be minus 326 kilometers per hour. So you can see here is this, right? With a negative sign. Very good, guys. Very good. Very good. Okay. And it makes sense. Why is negative? Because the distance z is also decreasing, as you can see, right? Over time. It's decreasing and decreasing over time, right? So that's why it came out negative. So it's not a typo. It's not a mistake. It makes sense, right? Decreasing over time. Okay, guys. Now I want you to try number 13. And then probably we will move to the last 2 forms. Can you try this? I will leave this in the top because there are a lot of steps, there's signs and stuff. Yeah, you can try this. Try this. It will help in your homework. Yeah, the equation is the same, right? The theorem of Pythagoras. Then you take derivatives in both sides. Then you replace what you have. You find what you don't have. That should be it. Yeah, we forgot to put here south, but we didn't use this really, south. Let's make it a little bit bigger here so everybody can see. Mm. Mm. All right, guys, let me start drawing. And if you finish up, let me know. Let me start with the drawing here. A good drawing always helps.
Professor, is it C?
Huh? Let me check, Matt, number 13. Excellent, excellent. Excellent, Miguel. Excellent, Matt. Excellent. Very good, guys. Very good. As you can see, it's very computational, but if you follow the steps, it should be excellent. Very good. So west, east, right? East. Very good. Again, they're talking about two planes headed to the airport that we can represent here by this intersection, airport there. And they say that one plane comes from the north at this speed, 184 kilometers per hour, this direction. And the other comes from west at this speed from the east, right? So from the east, from this side, right? So let's just remove this. Yeah, so from here, from the east, right? So that is at 210
Professor, you drew
kilometers.
the compass wrong.
Oh, sorry.
By
I'm so
accident.
sorry. Yeah. So sorry. I was right, I think, at the beginning. Yeah, it's just that west.
Never eat sour
Yeah, west
watermelons.
to be here.
Yeah.
Excellent. Yeah. Nice catch there. This is west. This is east. Yes, absolutely. Yeah. Excellent. Yeah, now it makes sense. So very good. This guy is approaching at this speed, right? 210 kilometers per hour. Excellent. And then the challenge is to figure out, right, at what speed or at what rate of change the distance between the two airplanes, right? This distance Z is changing, right? It's changing. And not at any moment, at this particular moment, right? When this guy is 33 kilometers away from the airport, and this guy is 22, right? At that moment, what is the rate of change of Z? And again, right, at any moment, the theorem of Pythagoras will help us here, because at any moment, given that this angle is 90 degrees, always x squared plus y squared will be equal to z squared, right? Z squared. Taking derivatives of both sides of this equation with respect to time, we take derivative with respect to time always for related rates, right? We explain that. Then this is going to happen. 2x derivative that comes to mind, and then we attach dx dt. Derivative of y squared. Derivative that comes to mind to y, but we attach dy dt, right? Because we're taking the derivative with respect to time. Similarly here, the derivative of this guy, 2z dz dt. Excellent. So now, let's replace what we have and let's find what we don't have. X at this moment is 22, right? 22. Yeah. What is this guy? Anybody could tell me what is dx dt at that moment?
Negative 210.
Excellent, right? Look, this guy, right, is changing at 210 kilometers per hour, but negative because it's decreasing over time, right? Decreasing, very good, excellent. Twice y now. Y is 33 here, 33 here. Multiply by this. What should be this? Anybody? dy dt.
184.
Yeah, but positive or negative, Miguel?
184.
Positive
Oh.
184 or negative 184? Which one?
Negative.
Aha, excellent, excellent, Miguel. Negative because it's decreasing, right? This airplane is approaching to the airport, decreasing over time. So negative 184. Excellent. Twice z. Z apparently is unknown, but in reality, z could be found because z is what corresponds to the hypotenuse when this leg is 33 and when this leg is 22. And that z can be found by using the theorem of Pythagoras, right? As 33 squared plus 22 squared, the square root of that, right? That's z. So z can be found. Take your scientific calculator, use square root function. Yeah, very good, very good. Yeah. Yep, yeah, that's it, right? That's it.
Yeah,
Excellent, guys.
39.66.
39.66. Excellent, excellent. 39.66, right? Let's write it down. 39.66. And this is being measured in kilometers. So believe it or not, guys, this is what you have to put in here, right? In here, right there. 39.66. And the last one, dZdt, is something that we really have to find, right? That's what they're asking you to find, right? All right, now again, I'm going to do this computation, guys, in one step using the calculator so we won't write stuff anymore. So I start typing this whole thing, and then this part will divide into this part, right? So let's do it. Okay, so 2 times. Start with 2 times the left part of the equation. 2 times 22 times negative 210, close parentheses, plus 2 times 33 times negative 184, right? All that, right? All that, highlight, slash, right? Divided by this part that goes into this, right? So 2 times 39.66, we said, right? 66, excellent. So that gives us 269 negative 0.59. Rounding this to a whole number, whole integer, we said to this part to a whole number, right? It will be 270, right? Because of the 5, 270. So negative 270, negative 270. So we can say that negative 270 is kilometers per hour will be the rate of change of z for this distance, right? Very good. You look through and it's here. Excellent, excellent, guys. Yeah, try to remember this method when you do your homework. They will talk to you about a police officer and a car running, or, you know, over speeding, I think, and you will figure it out following this, I think. And also I have attached a video to the problem. So in case you don't understand the problem, watch the 5 minutes video, it will be fine. All right, so now let's move to this last form that I want to secure. Is related to finance, application of this to finance. Let me explain to you number 14, and I will ask you to do number 15, which is similar, okay? So for number 14, they are saying here, assume that the profit generated by a product is given by this function, this profit function, P of X equal 4 times square root of X. So the profit function that some economists have figured out for this company, right, is given to us. We use it. Where X is the number of units sold, right? The more you sell, somehow the more profit, right? Very good. If the profit keeps changing at a rate of $700 per month, here they are giving you the rate of change for the profit, then how fast are the sales changing when the number of units sold is 1,500? Round your answer to the nearest dollar per month. Okay, so in this case, we don't have to figure out a relationship between profit and the number of units sold because it's given. They are giving it to us, right? Then we just go ahead with step 2 and say, okay, I'm going to take derivatives of both sides of this equation, right? Yeah, profit here, derivative with respect to time of this 4 times the square root of X. Now, this guy is just dp dt, right? And it's even given here, right? It's $700 per month. So don't worry about this part, but this part deserves attention. First, I need to notice that the number 4 is just a constant. So I take it outside the derivative and I focus on taking this derivative, okay? With respect to time. But now recall, remember I gave you this result, right? In previous lectures, the derivative of the square root function in general with respect to X is just this in simplified form, 1 over twice square root of X, right? In simplified form is this. We're going to use this. So over here, I'm going to say, okay, dp dt, derivative of profit function with respect to time will be equal to what? 4 times what? This derivative following this should be what? 1 over 2 times the square root of X. That's the derivative that comes to mind using this, right? But since we are taking the derivative with respect to time, we have to attach dx dt, right? You follow, guys? You attach this guy. And then simplify a little bit and then just replace what you have and get what you don't have. 2 into 4 is 2. 4 times 1 is 4, right? Over square root of X times dx dt, right? Is what I get simplifying, right? Simplifying. All right, now remember, this guy is given, is here, $700 per month, right? The profit, the rate of change of the profit. So let's write it there, 700, right? It's 700, right? Yeah, then 2 divided by square root of X. But what is X? What is X? They say somehow this motion should be stopped when the number of units sold is 1,500, right? This is what you write here, 1,500. Yeah. And maybe I should highlight it. Sometimes students like to see where the quantities are coming from, right? We use this for this part. Yeah, very good. All right, now times dx dt. Dx dt is the only quantity that is unknown. We're gonna find it. We're gonna find it, right? But now, guys, to compute this, you can compute this partially, right? Write it down and then that into 700, right? You can do it any way you want. I'm gonna try to do this way. I'm gonna multiply by this radical square root both sides, right? So if I do that, this guy is gonna come here, right? So this guy that is dividing, sorry, on the right side goes multiplying to the left side. So I will end up with this, right? Follow? And you say, Professor, what did you do? Well, all I did was this. I multiply by 1,500 here, square root, right? Sorry. Let's go to the right. Yeah, and I multiply this also by the same amount. Square root of 100, right? Multiplying both sides, I get this. Yeah, very good. So now, dividing by 2 both sides, this should be just this, right? 350. And again, guys, you can compute this any way you want. You can follow a different method. So bottom line, this has to be this, right? Get this guy down. So 350 times a square root of 1,500, right? Excellent. And I get 13,555 rounded to a whole number, right? Because I see that choices are whole numbers. So rounded to a whole number this, and it will be 13,555. And in the end, you may attach the units is dollars, right, per month. Right? This is the rate of change of the number of units sold. They have to, right? So this one. Very good, guys. Very good. Can you try to do number 15 now? Try this. It's a nice example. Yeah, remember this is the equation. Let's write it out, right? As a hint, P equal to a square root of X. Take derivatives on both sides of the equation and then do the math, right? And use the information, right? They're giving you these two pieces of data, right? The rate of change of the profit and the rate of change of the, not the rate of change, the value of X, right? At that moment. Yeah. So go ahead, do that. Just put it back. Yeah, that was good. Yeah, then I'm giving you these two. Yeah. Use that data. And also recall, I should write it perhaps here. Recall this result, right? That we have derivative with respect to X of the function square root of X. You have to have this written somewhere handy, right? When you take your exams, it's very useful because otherwise you have to put here 1/2 and take the derivative using the power rule will take time. But this is the final result of this derivative. Use that too.
Professor, I got A.
Let me see. Let's check. Excellent. Very good. I see you have mastered this part. Okay. Very good.
Word problems scare me, so it's a big
Don't
deal
be
that
scared.
I got this.
No, guys, you should never be scared, right? Fear is mind killer. Instead, just remain calm and look at your material. You have wonderful material. Look back to the notes, check the videos. Everything should be there. All right, very good. So let's do it together to see if we can do one more problem that I left without solving, but let's see. Very good. So we start, since we have the relationship between profit and the number of units that must be sold monthly. I have a question here from Deep, right? That this problem basically means in simple terms. Okay, yeah, I can explain. Yeah. Deep, what they're giving you here is the relationship between the profit of the company and the number of units that are sold per month in dollars, right? So clearly, right, the more you sell, the more money you will get as a profit, because if you graph this function, it's an increasing function, its shape is like this, right? This is something to notice. But here, the question is to find out the relationship between the rate of change of profit and the rate of change of the number of units sold. And you may say, why is that important? Yes, I think that's your question, right? Look, this is the if you graph this in your calculator, it's going to show you something like this, right? Profit here, number of X here. And if you don't follow what I just said, just take your grapher, P equal Y equal 2 times the square root of X, right? Yes, X raised to 1/2. All right, this is it, right? Yeah, that's the graph, right? It's a curve. That's what I got. Yeah, this is the graph of the function, right? Yeah, very good. They're increasing. Now, now the question is, right? This X could have any value, right? But they're asking you when this x reaches the level of 1,200, right? Sometime at some point, this will be 1,200. At that moment, right? They are asking you at that moment, what will be the rate of change of this guy, right? With respect to time. If you as a CEO decide that the number of units will be 1,200, what will be the rate of change of this with respect to time? What will be basically the cost of achieving this level of production, right? You followed it, right? First of all, right, is it going to be positive, negative? That would be good to know too, right? If it's positive, maybe it's worth to reach the level, but if it's negative, it's going to be decreasing the rate of change? Probably not, right? And also, once you find it, you will find by what number of units you will increase your number of units of production per unit of time, right? You follow it now? Better, kind of, a little bit? It's a rate of change that is important, right? Because if you are leading this company, first, yeah, it's like, this is a relationship between P and X. By taking the derivatives, we will investigate the relationship between profit and X. There is another relationship between these two, right? Let's see what it is. Yeah, let's comment on what we get. Okay, let's see. So here, the derivative of P with respect to T, the rate of change of the profit, how is it related to the rate of change of the level of production here? We will see. 2 comes out. Derivative of the square root of X following this is going to be 1 over twice square root of X. But since we are taking the derivative with respect to time, dx dt, right? I want you to notice this deep look. This is the relationship between the rates of change. It's a new relationship, right? Not this, is this, right? In simplified form, you can see that the relationship of the rate of change of the profit is 1 over square root of X times the rate of change of the level of production, right? Now notice, if you graph this, it's no longer increasing, right? It's something decreasing, I would say, right? It's a different relationship. Okay? So, and here you have to be careful because now instead of increasing over time, this will be decreasing over time, right? The more you increase this guy, the X, this will be less and less. You know, this is a decreasing function, right? If you graph it, right? So it's a new relationship between these rates of change. No, not increasing anymore, right? So, but we're gonna calculate what is it, right? It's still positive, but we will calculate how much is it, right? And that's the idea of this related rates problem. So this guy is given, they say, for this being 700, right? What should be the rate of change of X? So 1 over square root of X, the level of production that they want you kind of to consider as a way to take a picture of this motion, right? Profit is changing, X is changing over time, but when you should take a picture? When X is equal to 1,200, right? 1,200. Now, dx dt here, dx dt, this is what we're gonna find. Now, to find these guys, again, follow any rule you have. I am gonna use this. I'm gonna multiply both sides of this equation by this guy, the square root of 1,200, right? Here, the same. And I should get my value here isolated. Okay, this cancels this. Dx dt should be, dx dt is very carefully there. Dx dt equal to this multiplication, right? So let's get it in the calculator. A square root of 1,200 times 700. I get 24,248, right? 0.7. This time I can round it to 24,249, right? So 24,249 dollars per month. This is the variation on the production level that corresponds to a variation on the profit of $700, right? In order to get an increase of your profit of $700, you must increase on your level of production $24,249 per month, right?